Okay, so let's move on to the next use case now. So next we're talking about face detection and smile detection. Right? So in most of the digital cameras or even smartphones, right, smartphone cameras, there's a face detector, right? So anytime you're taking a picture of yourself or your colleagues, right, or your relatives, right, there's a kind of box that appears around each of the face. So this is called your face detection model, and there's something else also called smile detection, right? So I'm not sure if you've heard about this, but there's a camera. I don't remember which brand it comes from, but the idea is if you're taking a picture of a group of people, right, and if some people in that image are not smiling, then the camera will wait to take a snapshot until everyone is smiling, right? So that's a very good idea. The other idea is about closed eye stopper. I think that's what it's called. So there's a camera that continuously tracks eye movements of people while taking an image, and if during the instance of taking an image, if anybody has closed their eyes, then the photo would not be taken. Rather, there'll be a message that comes up saying that okay, this was a garbage photo, and then you need to take another one, right? With everybody's eyes kind of open. So yeah, these are again very important and very common use cases for from a computer vision perspective. And there are again models that have already demonstrated very good efficacy in terms of detecting faces or detecting smiles or detecting closed eyes and so on, right? So here we already see lots of commercial uses of computer vision technologies being embedded into mainstream products. Okay. The third is about object recognition, specifically in the context of retail industry and in supermarkets. So earlier we spoke about a problem called bottom of the basket loss. So what is bottom of the basket, right? So if you see this image here of a trolley with some products that somebody has bought, right? And at the bottom you see there's a box of Corona beers, I think, yeah. And I don't know what this guy was. Maybe I don't. Probably they were trying to steal it, or it was there by accident, right? So whatever the reason, what happens is this kind of products that are at the bottom, they usually get uh, they are not recognized by the cashier or whosoever is making the payments there, and ultimately, you can steal it, or maybe it gets lost, right? So it leads to a lot of revenue loss for your retailers. Now, what some companies have done, and the company is Evolution Robotics, what they've done is they've come up with a system, wherein they've placed a camera at the bottom here, and anytime you have a trolley that passes here, it takes a snapshot of this bottom of the basket, right? And it continuously recognizes images of products that should not be there, right? And if a particular object is there, then the person who's taking the trolley, the customer, they're charged for it, and yeah, the retailer essentially gets the money for the item, right? So this use case in itself has prevented losses worth millions of dollars for retailers, right? So again, this is powered by a very common computer vision technology called object recognition, and these systems have again proved to be very successful in commercial settings, right? And yeah, the name of the company is Evolution Robotics, and I think the product name is Lane Hawk, right? Okay, now computer vision also helps a lot in terms of biometrics, and a very famous use case of vision-based biometrics is this is the case of this Afghan girl. So on the left-hand side, you see a very younger version of this girl, of this Afghan girl, and she became very famous. I'm not sure for what, why she became famous. Probably for some social issues, or raising some social issues there. But after a point in time, people lost track of her, and then a lot of like 20, 30 years later, there came an image of this lady on the right hand side, and people were able to identify that the lady on the right is the girl on the left by looking at the patterns of her iris, right? So essentially somebody who went into obscurity over a period of time kind of was recognized back, and this was enabled, or this was made to have this was enabled by using vision based biometric systems. Okay, So those are like the couple of very common, or very common use cases for computer vision, especially in commercial settings. Now there's a lot of other use cases also that we have obviously not skipped, but I want to like quickly cover what are the common tasks. And when we say tasks, we are kind of talking about the technical part of things, not the business use cases. So in terms of tasks, we have three main categories of tasks in computer vision. So first is image classification. So image classification is very similar to a normal machine learning classification model. The only difference is that the input here is image instead of tabular data or NLP data, right? And within image classification, we have either binary, which is 0 and 1, or multi-class classification, or multi-label, right, classification. There could be another one which I've not listed here, which is multi-class and multi-label. So what is the multi-label part? I think that's slightly interesting for many folks. The multi-label is basically anytime you have an image, right, and the image can belong to more than one category in itself, right? So uh, one use case that comes to mind is that there was this competition on Kaggle, which was around identifying the class labels uh, in the satellite images of Amazon rainforest, right? And I think what they wanted to do there was to understand what kind of deforestation has taken place, what kind of afforestation has taken place, what kind of illegal mining activities might be taking place at specific places, right? By looking at the satellite image, and any given image was had more than one label. So you had, say, as far as I remember, you had things like agriculture, you had things like mining, and some other categories, swamps I think were there, right? So you have more than one label or one category in any given image, right? So those kind of things are called multi-label classification tasks. The other thing is about object detection. So if you look at the snapshot posted on the right hand side, the so snapshot basically shows you some balloons in the air, and object detection is when you want to basically detect the balloons and draw a kind of bounding box around them, right? The bounding box is basically a rectangular box that is around the center of the object, right? And you try to make it as tight as possible, basically touching all the corners. And this kind of task, when you want to do an object detection or draw a bounding box around stuff, that is called object detection. The third is segmentation. So segmentation is very important. In fact, not just segmentation. In fact, let's talk a bit about object detection, right? So object detection is very important in the context of autonomous vehicles. So for example, if you're building an autonomous vehicles, you definitely want to identify what are the items on the street, right? So things like trees, cars, pedestrians, right? You want to be able to identify them and also identify their locations, right? And how do you identify their location is by doing this bounding box kind of thing, right? So all this information needs to be fed in real time to the processing units of the cars, and then they can take particular evasive action, or decide the future course of the movement. Yeah, then we were talking about segmentation. So segmentation is of two types. First is your instance segmentation, and then we have semantic segmentation. So what is semantic segmentation, which is slightly more simpler than the instance segmentation? So semantic segmentation is uh, when you have these objects, right? And all you want to do is basically do a pixel-wise classification, right? Based on the category. So category in this picture would be balloons and say not a balloon, right? So you want to identify the pixel that form part of this object or category, which is balloon, and everything else is non-balloon, right? So here you can see uh, all the balloons or pixel level classification is in blue, and everything else is actually, so we don't care about the other stuff. Now, the important thing to note here is that we are not differentiating between the various balloons that we have, right? So I have a big balloon in between, and then we have smaller ones on the side and so on. But there's no distinction being drawn on in terms of the different balloons that are there, right? So that's where instance segmentation comes in. So instance segmentation is basically not just identifying not just making pixel level classification, but also identifying the various instances of that class, right? So here you see all the balloons, they're identified by doing a pixel level classification, and are also identified by means of different colors, right? So, and when I'm saying different colors, it inherently means that I have to do a bounding box kind of prediction also, right? Because I need to understand where these different balloons are. So the big difference between semantic and instance segmentation, which quite a lot of people get confused with. The big difference is in semantic segmentation, you do not differentiate between the various instances of the same object, while in instance segmentation, you do differentiate between the different instances of the same object, right, or the same class. Right. In our context, different balloons, they are identified differently, and the bounding boxes are also identified. Now, obviously, since instance segmentation task is slightly more complex, it is obviously relatively harder to do than as compared to, say, semantic segmentation. So we'll not talk about what models are used in each of them, but if you want to check out the details, you can obviously search over the internet. There's a lot of stuff over the internet for doing any of these exercises. Okay, so I now quickly want to cover one key ingredient of the computer vision models. So at the beginning, we spoke about how we have cracked one big code of one big puzzle of doing efficient computer vision models, right? And that one thing is called convolutional neural networks. And what are convolutional neural networks, or CNNs, as we call them? They're basically a special type of neural network which incorporate the fundamental aspect of vision, right? The fundamental aspect of vision based on feature creation using localized vicinity aspects and pooling, assembling those later on for a macro view, right? So in CNNs, what you do is you basically, if you have an image, you try to things, and then if you pick a pixel, right? You try to analyze things that are closer to that pixel. You don't want to go too far away. You try to analyze things that are closer to each of the pixel, right? And then you extract some insights from those nearby pixels. And obviously, over a period of time, you refine these insights also. And period of time meaning over a period of multiple neural network layers. But essentially, the idea is you pick some nearby group of pixels, you analyze what is the object contained here, what is the context here, and what are the local features. And then at the end, based on the task that you're trying to do, you pool all these features to get a kind of global or a macro level view, right? So here in this picture we see, so there is this input image of, say, 28 by 28 by 1. So by 1 essentially means it's a grayscale image. And then we are doing some convolution operations. So we'll not go into what these convolution operations are, but yeah, that could probably be reserved for some future sessions. But these are the crux. This is basically where we come to the crux of things, right? So this is what CNNs are doing. So they are basically creating a lot of feature maps, and these feature maps exploit this principle of kind of looking at things, that are closer to each other. And then at the end, you can see we have this fully connected layer, which is what is exploiting this, nearby features to get a global macro level view. And that is the essential kind of concept of CNNs. Obviously, there are a lot more details to be spoken about here, but we are kind of out of time. So we'll keep those things for the future sessions. But yeah, if you do have any questions, feel free to reach out to me over the channels that I've specified, either over LinkedIn or over emails. And yeah, I've also listed down some more details. So what are the typical libraries? So you have PyTorch from Facebook, TensorFlow from Google, and then there are a couple more. So MXNet, Caffe, and Gluon from AWS. And what are some of the common data sets? So in computer vision, we have two very common data sets that are used for benchmarking purposes. So one is the Cypher 10 or Cypher 100, and the other one is ImageNet. And then at last, the transfer learning models. So we have already spoken about this, basically the ability to create models on larger data sets and then leverage those for your particular task, right? And those larger data sets are generally the ones that come from these two sources. So Cypher and ImageNet are the ones. Yeah, and the references are also posted here. So yeah, thank you very much, and have a nice learning experience here. Thank you.